Welcome students of MSc Final in this e-lecture. In last lecture we have discussed about the structure determination of menthol. Now we summarized all reactions that we have discussed in last lecture. In this way we have elucidated the structure of menthol on the basis of simple chemical method of analysis. The investigation starts with the determination of molecular formula of menthol. From the molecular formula, we determine the 1 degree of unsaturation. Then the nature of oxygen was proved to be alcohol by its monoacetate derivative reaction. Then by chromic acid oxidation, its nature of secondary alcohol was found. Then skeleton nature of menthol was proved by its reaction with hydrogen iodide reduction as well as dehydrogenation reaction, which gives paracymene. In the next step, we determine the position of hydroxyl group on the basis of oxidative degradation reactions with KMnO4. In this menthol, on oxidation with chromic acid, forms menthone, which on further oxidation with KMnO4 leads to 3-methyl adipic acid. And the formation of this 3-methyl adipic acid is only possible when we assume the structure of menthol is like this, shown in the figure: a monocyclic secondary alcohol or paramenthine skeleton. Therefore, in this way, with the help of variety of simple chemical reactions, we can determine the structure of menthol. Now, last but not the least, we come to the synthesis of menthol. This slide shows the strategy of synthesis. It is a questionnaire which can be asked in the examination. Now we take the synthesis. In synthesis of menthol, the starting material is metacresol. The metacresol, when we treat it with the isopropyl iodide, we get menthol. In first step, metacresol on reduction gives 3-methyl hexanol. This compound, 3-methyl hexanol, this 3-methyl hexanol on reduction with chromic acid forms 3-methyl hexanone. In the next step, we have to introduce isopropyl group. For that, we react 3-methyl cyclohexanol with diethyl oxalate and sodium metal. Then we get dicarbonyl type of compound, this type of compound. When this compound heated, it converts into beta keto ester by the elimination of carbon monoxide. This beta keto ester reacts with sodium ethoxide followed by alkylation with isopropyl iodide. In this way, we reach to our main skeleton of the molecule. And this compound on reaction with sodium ethoxide leads to the ring opening skeleton reaction and a dicarboxylic acid is formed. This dicarboxylic acid. This dicarboxylic acid forms a calcium salt, and if this calcium salt distilled, we get menthone. And menthone on reduction, we get menthol. This final compound, menthol. So This is a very interesting synthesis of menthol involving very simple starting material like metagresol as well as isopropyl iodide. Now let us discuss the stereochemistry of menthol. In the structure of menthol, there are three chiral centers. 1, 2, 3. And because of these three chiral centers, the possible stereoisomers for this molecule is 2 raised to power 3 or 8 stereoisomers. Therefore, menthol exists in 8 optically active forms. And these 8 stereoisomers are shown here. In other words, we can say menthol exists in 4 pairs of enantiomers or 4 racemic modification. And these 4 enantiomers are menthol, isomenthol, neomenthol and neoisomenthol. Menthol is having its 2 isomers. Similarly, isomenthol, neomenthol and neoisomenthol also have two isomers and enantiomers. Now this menthol is diastereomers of isomenthol, neomenthol and neoisomenthol. Similarly, isomenthol is diastereomers of menthol, neomenthol and neoisomenthol. The naturally occurring menthol has the configuration 1R, 2S and 5R. Since the menthol is a 6-membered ring, we can draw its chair conformations as shown here. While drawing the chair conformations, the bulkier isopropyl group will prefer to occupy the equatorial position. So in all the cases, we have written the isopropyl group in equatorial position, and accordingly we adjusted the position of hydroxyl group and methyl group. In menthol, all substituents are in equatorial position, whereas in the remaining at least one substituent in axial position. In isomenthol and neomenthol, there is only one axial substituent, whereas in the case of neoisomenthol, we are having two bulkier substituents which are axial to each other. And because of 1,3 diaxial interaction, the isomenthol, neomenthol and neoisomenthol, they will be unstable as compared to the menthol. As per the stability is concerned, menthol is most stable due to absence of 1,3 diaxial interaction. However, one Gaussian interaction is present. Neoisomenthol is least stable due to 1,3 diaxial interaction between two bulky substituents, hydroxyl group and isopropyl group present in axial position. Therefore, the stability order is menthol is most stable, then neomenthol, then isomenthol, and neoisomenthol is the least stable. Therefore, in this way, we have learned the chemistry of menthol. Thank you very much for watching the video.